In this video, we'll be solving this problem. I'm looking at the space of polynomials of degree 3 or less, and I'm going to define an inner product on it by multiplying the values of the functions at -1, 0, 1, and 4. I'm going to prove it's an inner product, so I'm going to prove all four properties, and then I'm going to use it to find the length of x squared plus 1 in this inner product space. So we have four properties to prove. Let's start right away. So the first one, I need to prove that if I switch the order of P and Q, it doesn't change anything. Well, since these are products in R, they wouldn't. The order doesn't matter, so that's going to be Q minus 1, P minus 1. Let's just put 3 dots. Q of 4, P of 4. Those are real numbers. I can switch them. And so I get the same thing as P of x, Q of x. Alright, so we can switch the order, that works. Second property, if I multiply 1 by k, the k can come out of the inner product. So let's try this. Alright, so if I multiply p by k, well, I'm going to get kp of minus 1 instead of just p of minus 1. Q of minus 1, and then kp of 4, q of 4. Now this just means multiplying by k, so again I can factor it out of each one. And what I'm left with is the inner product, well, the product of P and Q, and so I get that K comes out of the product. Third property is if I have a sum in one of the spots, I can split it. So let me put P plus Q here, and then R, so this will be P plus Q minus 1, R minus 1, and all the way to P plus Q 4, R of 4. Right, now P plus Q of 4 is P of 4 plus Q of 4, and so what I'll get is this. Now I can multiply the Rn, and I'll get P inverse of R of minus 1 plus Q minus 1, R of minus 1, and so on, up to P of 4, R of 4, plus, actually let me write them here. Now if I take all the p's together, I'm going to get the product of p and r. If I take all the qr's together, I'm going to get the product of q and r. Alright, so the sum here splits and I get the sum of the inner products. Alright, the fourth and final property is about the sign of the products when I apply it to the same element twice. So if I look at what PP gives me, I'm going to get P of minus 1, R of minus, P of minus 1, and I'm going to get P of 4, P of 4, and so I get the squares of all of these elements. Each of them would be positive, so as a whole they're positive. Alright, so the inner product of P with itself is always positive. That's important because when I'm starting to talk about the norm, I want to be able to take the square root of these. Now the second part of property 4 tells me when this is 0. So I want to look at when PP is 0, and it's going to be 0 exactly when P inverse is 0, P of minus 1 is 0, P of 0 is 0, P of 1 is 0, and P of 4 is 0. So now if I'm thinking of P of x here, this is a polynomial of degree 3 or less, which has 4 zeros. That means P is 0. Alright, so that proves one direction. The other one is pretty trivial, but let me do it nonetheless to be complete. The other direction, I'm going to assume P is 0. That means PP is P minus 1 squared plus P of 4 squared. All of these are zeros, and so I get 0. For this evaluation type inner product to work, I need to make sure that I have at least one evaluation point more than I have degrees. So for P3, I needed at least 4 different points. I use minus 1, 0, 1, 4. The points themselves don't matter much. It will give you an inner product anyways, but I need at least 4. If I have 3, then there are polynomials that have 3 zeros but are not 0, and so this last part here wouldn't work. Alright, so that proves that we have an inner product. Now I need to compute the norm of x squared plus 1. So I'm going to look at what happens when I take the inner product of x squared plus 1 with itself. This is going to look like that. So I'm going to take the value at minus 1. The value at 0, the value at 1, and the value at 4, and I'll square them all like I've seen over here. So that's going to be 2 squared plus 1 squared plus 2 squared plus 17 squared. And so 4, 5, 9, 17 squared. I got 298. Alright, so this inner product is the square of the norm, so if I want the norm itself, I just take the square root, and that will be the length.